Here's the light bulb problem. There are so many things wrong with this problem, I'm not even going to have time hardly to tell you all of them. We have a light bulb with a tungsten filament, 40 watts, 120 volts, at 1500 C. The filament is at 1500 C. That's why it emits light. How long is the filament if you're given the diameter, and what is the resistance of the filament when it's at room temperature, not when it's at 1500 C? So first, problem with this is nobody uses light bulbs and filaments anymore. So let me draw that for you, just so you'll know. A light bulb is this thing, it's kind of round. And down here there's a screw-in part, and it's got a little button on the bottom, and the sides, the threads, are actually electrically isolated from each other. So it's two electrodes coming in, and then connecting them is a big, curly, long piece of tungsten like that. Tungsten has a high resistance, and it's very long and thin, so there's a big resistor here, and you dissipate all of your joule heat, all of the electrical resistivity dissipates its heat, heats up the filament to a very high temperature and emits light. All right, so this is really just a coiled wire. Okay, now let's stretch it out and see what we have, and then we have the geometry that we understand. We have a long wire of length L and some cross-sectional area A. That's what we need to work the problem. So you're given these electrical characteristics and asked how long is the wire. So you got to realize that A, or the length, is related to the resistance of the wire, and R is related to power dissipated. So we start with our power, we say P. Well, the one you usually know first is IV. But remember, I always tell you, look at the three versions of it and see which one is maybe the most useful when doing the least calculations. These are just the same equation where we use V equals IR to substitute in. In this case, we have the power and we have the voltage, we want the resistance, so I would probably choose this one. So we solve this for R. I'm doing algebra here. R is V squared over P. So the voltage is 120 volts. That's another problem with this question, is it's actually AC. We're pretending it's DC. It's slow AC, so it's pretty close. 120 volts over squared, right, over the power was 40 watts. And that comes out to 360 ohms. All right, so we have the resistance of the filament at 1500 degrees C to get started. And how long is the filament? Okay, yes, so let's keep going now. So now if we say how long is the filament, well, we'd say then 360 ohms is rho times L over the area. And we know the area, we know it's pi r squared, and we have D, so we could plug in. But the question is, what is the resistivity? If you look up the resistivity of tungsten, you're going to find that it's 5.6 times 10 to the minus 8 ohm meters. But the number you find in a table is usually at room temperature. It's not the value when you're at 1500 degrees C. So the next problem with this question is that the book doesn't tell you how this changes with temperature. It's not complicated, but the book doesn't really go into it. I talked about it in the lecture. I guess when they wrote these problems, they forgot it's not in the book anymore, or maybe we added this, I don't know. But the fact is, the way this changes with temperature is that the resistivity at some temperature equals the original resistivity at some other temperature, a known temperature, like room temperature, times 1 plus alpha, times the resistivity at T, and then this is the resistivity at T naught. So R naught, or resistivity naught and T naught don't have to be room temperature. They could be any temperature where it's known. But usually you think of this as where you plug in the room temperature value you looked up, and then you get the high temperature value, rho, at some high temperature, and you just need this number, which for tungsten is well known to be 0.0045. All right, so using that, we can then say that rho equals, okay, rho naught times 10 minus 8 times 1.0045 times T minus T naught is 1500, and if this is at room temperature, that's like 20. Okay, So this is all now just numbers. This comes out to be 6.66, and plus 1 is 1.66 times that. And you get the real value of the resistivity that you need, which is, let's see, did I write it down? 43 times 10 to the minus 8 ohm meters. So you can see it's higher. At room temperature, it's only 5.6 times 10 to the minus 8. Then it goes up to 43 times 10 to the minus 8, as it's supposed to. This, by the way, is a simple linear relationship. It's not really as complicated as it looks. It's just written this way. The equation of the line is written this way, so you can get the new value from the old value at the old temperature. It's really just the equation of the line, where that's the slope, and then the intercepts are hidden there. Okay, here's the problem, is the book doesn't use 43 times 10 to the minus 8 ohm meters. The book solves this part by saying the resistivity at this high temperature is 50 times 10 to the minus 8 ohm meters. I'm not sure why. It's kind of strange. But if you use that number, you say, okay, 360 equals 50 times 10 to the minus 8. We'll do it all MKS, L that you're looking for, pi, and the radius is 0.0195 millimeters, also known as 19.5 microns, times 10 to the minus 6 meters squared. All right, so 360, you multiply by this, you divide by this 50 instead of 43 for some reason, and you get L equals 0.86 meters. And a lot of people struggle to find that value, probably because they're so smart, they calculated the correct resistivity. So how they got 50, I don't know. Clearly you're not rounding 43 to get 50. I doubt you would do this. It would round to 40. So my guess is they either had the wrong value or an unusual value of the temperature coefficient or an unusual value of the room temperature resistivity. I'm not sure why. There's no tables in the book, so I'm not sure how that happened. Now, let's see. So the second question is, what was the original resistance of the coil at room temperature? We calculated it at high temperature. It was 360 ohms, just from the electrical part. So I want to show you an easier way to do this. You could say, oh, I got the resistivity now, and I got the geometry, and I plug it in. But one thing I want to show you is that this equation is for the intrinsic resistivity. But if you keep a constant geometry of a wire, it can also apply to the extrinsic resistance. We could write this, we could turn this into resistance by multiplying it by L over A. We could turn this into the resistance by multiplying it by the same L over A. Therefore, we can just say the resistance at some temperature equals the room temperature resistance times the same 1 plus the same alpha T minus T naught. Exactly the same. Now, in reality, the geometry will change because it'll expand. Okay, let's not get into that. Okay, so if we do this, then we can solve this and say R at high was 360. R naught is what we're looking for. All right, 1 plus 0.0045 times 1500 minus 20. Right? That doesn't look so hard. How could we possibly get that wrong? 360 divided by 7.66. And what do you get? You get R naught equals 47 ohms. R naught equals 47 ohms. And again, the book doesn't agree. People plug that in, most popular answer. The book says, no. The book, R naught, room temperature, is 40 ohms. So you as a student, it's your job to throw up your arms and say, what is wrong with this book? Why did I pay for this? It's my job as an instructor to figure out what did they do wrong. There's an opportunity to figure out what they did wrong. Because here, it was unclear if they had an incorrect value of the room temperature resistivity or the temperature coefficient. Unclear. But now, suddenly, we can figure out maybe what they did wrong. Because we don't have to worry about the room temperature resistivity here. We're finding it here. This number we got just from the electrical properties. Couldn't screw that up. So if we look at this, we could back calculate and say, okay, if this is 40, 360 over 40, do 1, etc., and say, what did they use for that? What did they use for alpha? Guess what you get? 0.0054. I think when somebody typed it in, they switched their 4.5 and their 5.4. Because sure enough, if you use 0.0054, you get the book's answer, 40 ohms. And guess what? If you solve this now and put 0.0054 here and the standard 5.6 here, you get their value, 50 times 10 to the minus 8 ohm meters. So that's the answer to the mystery, is somebody switched the two different